What I'd like to talk about today is some work on sort of what's going on under the hood when we were analyzing large social graphs. So actually this started when I was at Yahoo. So I had been doing randomized matrix algorithms, as you heard at the time, and they were useful for a lot of things, and there was a lot of interest in machine learning in various sorts of statistical techniques and machine learning kernels and low-rank decompositions and these sorts of things. And the methods performed very, very poorly for doing certain problems that I'll mention on looking at social and information networks. So this was at Yahoo, so it was advertiser bidded phrase graphs, but it was also social graphs. This was, I guess Facebook probably existed, but it was probably still in a garage at the time. So, I mean, this is way back when. And in order to arrive at certain conclusions, we sort of had some statistical techniques and reinterpret sort of old and existing techniques. And so I'd like to sort of cover two things. One is some just facts about what some of these data sets look like, because I think they're very, very counterintuitive. But in order to establish those facts, we needed to sort of invent new algorithmic methods and have a very sort of fine understanding of the statistical properties and mathematical properties underlying these techniques, much sort of more fine-grained than you typically find. And so that may give you sort of an inkling as to sort of interesting mathematics that arises in this class of graphs, right? So I can't claim that Facebook's valuation is because of the interesting mathematics in their problems. But at least at this institute, you know, a question might be what's the interesting mathematics that you can distill out of some of these problems. So I'll sort of try and allude to some of those. And the second thing, which is related to that last observation, is essentially we had to use sort of what I'll call spectral methods, and I'll say what I mean by that. And those have strong connections with eigenvectors, as you may know. And if you think about eigenvectors, the intuition people have is that they're very global things, right? If you do signal processing and you do a bandpass filter, you might want to remove the high-frequency components because those are pretty localized, and the low-frequency components very slowly over your data set. Now, that's actually true if the data set's nice in various ways. And it's not true if the data set's not nice, say a social graph. And to oversimplify a very sort of large and complicated story, the sort of key idea has to do with whether the eigenvectors are localized. And so by localized, I'll mean most of the mass is on a small number of nodes. And if they're localized, a lot of algorithmic and statistical methods break down. There's a lot of interesting technical and sort of mathematical questions that will arise. And so I want to cover that. And in addition, sort of related to that, is there's this notion of regularization, where you have sort of ill-posed problems, and so you change the problem to be a little bit nicer or more robust to the data. And there's various ways to do that. But the way that's going on here is that we're not going to sort of explicitly form the regularization, but we're going to ask sort of implicitly, is there regularization going on inside these algorithms? Directions that arise there. So before I get to that, so I may not get to the third bullet, depending on time, so I'd rather cover two things in more detail rather than three things in less. And the room is reasonably large, but if there's people if you're totally lost, raise your hand taller, because I'd rather make sure that a small number of things are clear than a large number. So I want to talk a little bit about these social graphs, and then I'll talk about eigenvector localization and how sort of a key idea at sort of the think of this large-scale data stuff that I'll spend a few slides on as a forcing function. There's a lot of data out there, and there's applied people that want to do something with it. But methods people, mathematicians and statisticians and computer scientists, all have their sort of historical baggage that they come with, they happen to learn. But these sorts of questions sit right at the fault lines between sort of mathematics and computer science and statistics. And so the eigenvector localization, implicit regularization, scalable algorithms that I'll be talking about sit right at sort of the fault line between those areas. Okay, so big data and massive data. So if someone says they're doing big data, you should ask them if they were doing it back when it was just massive. So we started the MMDS meeting in 2006, and we actually thought a lot about the name at the time because we knew that we might be on the cusp of something that was going to get big. And so we decided the name massive data floating around. We decided to call it modern massive data sets because that seemed like it was sort of a little bit buzzword compatible. It had a nice ring to it, the MMDS meeting. And we did this in 2006, and it was clear it was a success. And we did it in 2008 and 2010. And by then, we had heard this thing called big data, but it was in really technical venues. And then by 2012, it's on the cover of these sorts of magazines. And at that point, we knew that the big data people had a better marketing department than we had. And so we had lost the game, as it were. So, big data, what is it? I mean, the great thing about big data is it's sort of a content-free word. It can mean anything to anyone, and different people mean very, very different things by it. So it's hard to get at what you mean by this. One of the nicer descriptions I saw was in the New York Times back in 2012. The article was The Age of Big Data, and they said, what is this thing? What is this thing, big data? And so it's a meme and a marketing term for sure. So, once you're on the cover of magazines like this, that's just a given. So you have to just take that there's a lot of fluff there. But it's also shorthand in some sense for advancing trends in technology that open the door for a new approach to understanding the world and making decisions. So essentially, the way to think about this is that you can measure things about the world. And this is the properties of people's genomes. This is properties of the stars on the other side of the universe. I have a phone somewhere. It's off now, so I'm in the battery. But if it wasn't off, someone would know that I'm sitting here and my bag's been stationary for an hour, and then I pick it up and walk up and down a flight. They measure acceleration, lots of things at incredibly fine levels of granularity. Whether you click on web pages, every time you click on a web page, 50 or 100 lines get written to files at various places. And so measuring the habits of people, the purchasing patterns, all these sorts of things at very, very fine levels of granularity. It's important that big data are big, not just because you have a factor of 10 more data. So if you're a statistician that says I have some model and go to some asymptotic limit because I get a factor of 10 more data. Big data are big not just because you have a factor of 10 more data, but a factor of 10 different data, right? No one goes to the effort to generate a factor of 10 more of the same. Generated at finer spatial resolution or frequency resolution or generate different data. So it's a factor of 10 different data, different times, places, different resolutions. So this is a slide I like. Proverbial sort of elephant in the room. So there's this anecdote about the blind men are sort of groping at the elephant, and some people say, well, it's wiggly and a little bit sort of hairy. The hair on the tail has a certain texture, and there's a long trunk thing, and the ears are flappy, and this goes coarse in the back, and everyone's making a very local observation about what they see, not realizing that this is in fact a big elephant. So the proverbial elephant in the room is that how do we view big data? And the poor elephant just says, can't anybody see who I am or want to be? So this is your big data. And if you're a computer scientist, you might say just, wow, I need a bigger supercomputer, I need a bigger machine. A statistician just says, I got a positive model. A machine learner might say, the data's noisy, I need to do regularization. If you're a computer scientist, you might just say, geez, it's big, I need fast algorithms. Data scientists are a term that's used these days, and just say the data's messy, so I have to clean it up. So everyone has sort of a local view. So you can take a step back and get a better understanding of what sort of the data is by itself. So to oversimplify, I think so in this slide we had 5, I think, areas. There's a number of others depending on how fine-grained or coarse-grained you want to talk about it. To sort of oversimplify a complicated story, I think the lead axis of variance, if you want to say how are people thinking about the data, is going to be the following. For lack of a better term, I'll say computer scientist or algorithmic perspective. And that's basically the perspective that you'd adopt if you were trained in computer science. So things are changing a little bit now, so say computer science before 10 years ago. But basically the perspective you'd adopt if you were trained sort of classically, historically in computer science. And a statistical perspective, this is sort of formalized most formally in academic statistics departments, but really think of it as just the perspective that everyone else adopts. And the key thing is that if you're a computer scientist, the data are a record of everything that happened. Right? You develop algorithms for database computations or whatever, and you want to chew on the data in front of you. That's all there is. There's no world out there. You chew on the data in front of you. And the goal is to find interesting patterns and associations. Maybe what you want to compute is intractable under the models of data access, and so you develop some sort of approximation algorithm within a factor of 2 of something. So the point is that the data is everything there is in front of you. There's no need for regularization because there's no noise. The data is everything. So statisticians and natural scientists and finance people and economists, basically anyone else, and you see it in a lot of applications now where computer scientists are working, and we want to make some prediction about what people are going to do on the web or anywhere. Think about the data as a particular noisy random instantiation of some underlying process going on in the world. Data are so valuable because they're the only stories you tell yourself. It's the only insight you have into the world. And the goal is to make claims about about the world. So here you're studying computation per se, but here you're making claims about the world. And computation may or may not be a useful tool. And in particular, you want to make inferences about data that you have not seen yet, but about data that you're going to see tomorrow. By positing some sort of model. You may write that down as a particular form of model. You may just have in the back of your mind that stars and proteins behave in certain ways and have it written down informally. But positing some sort of model that describes some sort of variability around a deterministic model. So here, the data is all there is. So as big data get big, big data sit in databases. Databases are built by computer scientists. So where you're storing the data, how you access the data are built by people who think this way. And everyone else wants to think this way and needs to make claims about the data, and they're working with tools that maybe are not ideally suited for what they're doing. So the question is, can you tie these two together? So these are two very different perspectives. In statistics and natural sciences, scientific computing, downstream applications, problems involve computation, but the study of computation per se is secondary. And in particular, it only makes sense to develop algorithms for something called well-posed problems. So a problem is well-posed if the solution exists, it's unique, and it varies sort of continuously with the problem parameters. Now, you might say, why would anyone think of solving ill-posed problems? I mean, it only makes sense to solve problems that are well-posed. It's not very good to solve things that don't exist. Is it unique? You may find it awkward if you're trying to solve something that isn't unique. And if the problem varies wildly, if you change the 16th digit of precision, that's a little awkward. So in spite of that, a lot of people want to solve ill-posed problems. So an example of an ill-posed problem, or a problem that's not robust with respect to tweaking the problem parameters, is, say, the least significant digit in your bank account. You have some number of dollars or pesos, wherever, in your bank account. And you have, 57,412.17 units there. And if you add a check for $100, you're going to want the bank to increment that number by $100 to 8 significant digits. You're not going to be happy if the bank says, well, there's a lot of noise in the world. Let's just round it down to the nearest digit. So the database industry grows up around this, right? You want to do it. You want to do it online. You're going to be upset if you deposit money now and it's not there tomorrow, so you need to do it online and in real time and so on. So there's a lot of value in solving not well-posed problems. The database industry grows up around that. So in computer science, it's easier to study computation per se, in and of itself in discrete settings. So you get Turing machines and logic and complexity classes, very non-continuous and very brittle things. So in a sense, the theory of algorithms divorces computation from the data. If you're a computer scientist, or you do applied math of the form that appears in discrete math and computer science, you're thinking about the data this way. And if you make claims about algorithms, you think of the algorithm as a function that maps input to output with no claims about noise properties of the input and output. And that's just a very, very different way. So first write down a model and think about computation. Maybe engineer the robustness into what you're doing. First, think about a fast algorithm, and then ask sort of what it means later. So this is high level. This manifests itself in sort of a lot of ways. And so what we're talking about sort of sits right at this interface. So we're going to be wanting to look at social graphs, and I want to describe some of their properties. And a graph is a discrete thing. And so you can run approximation algorithms from computer science on that. And the answer is, do you get anything meaningful? Of course, you can think about the graph as a discretization of a continuous place. Scientific computing and a lot of areas of applied math do that. And a lot of algorithms are developed there. The question is, what if any relationship is there between the two? And you can imagine there's some cross-fertilization. These people use that and vice versa. But when you get really down to the details, there's a bit of a culture clash there. Because if I want to make a claim, or if I'm going to use this in a statistical setting, I might want to say that I have enough data points that I can take some asymptotic limit. Or that the data is sort of redundant enough that I can do recursive bisection, right? If I'm going to do a recursive bisection to get good properties, I'm going to not be happy if my bisection, instead of splitting the data into two pieces that are 50-50, I split the data into pieces that's 99.9 and 0.1, because my recursion depth is not going to be so good if I do that, right? So we'll see some examples of this. And at the heart of some of those differences is going to be this notion of regularization. And the modern theory of approximation algorithms, as formed in computer science, essentially involves embeddings. And what we want to say is that the embeddings are ways to take intractable combinatorial things and render them nicer. And so implicitly, they're implementing regularization. They're doing it in a very different way than you would typically think of doing it in machine learning or statistics, but they're doing that in a certain way. And so I'll give you an example of that. And sort of at the heart of this is that something called local spectral methods, and we'll see that that's going to be related to the notion of eigenvector localization. All right? So before I get into that, is there anyone who's sort of wildly happy or unhappy? Or, all right. All right, so network data. So there's lots of graphs out there in networks, and networks is a popular term. And this work grew out of some stuff when we were looking at social and information graphs. There's a bit of a difference between networks that are given to you and networks that you construct, in the sense that if they're given to you, you have to work with what you're given. If you construct them, you have some knobs to play with. Now, in fact, if they're given to you, someone had to construct them, and they had knobs to play with. It's not like there is the Facebook graph or the web out there. There's a lot of engineering decisions. I'm going to gloss over a lot of those today. And I'm going to gloss over them because if you go to people and say, give me your graph, and they say, how should I prepare it? The answer is, I don't care. Prepare it the way you would prepare it in your application and give it to me, and I'll run an algorithm on it. I'm a computer scientist. You're the applications guy. And then, then I don't engineer my biases into you. So we have seen that if we do that, you get some very bad results, and I'll talk about that. Now, you could say, well, I'm in an application, and I want to engineer the graph. How do you engineer the graph? The data is a bunch of feature vectors, and I do it with some nearest neighbor rule, and there's a million of these. So I engineer the graph, and I want to run graph algorithms on it. Now, if you engineer the graph and you have 10 different knobs, you have a pipeline, you have a nearest neighbor rule, you have to normalize some way. Do you use k nearest neighbors or epsilon nearest neighbors? Do you threshold here? Do you do this? There's a whole pipeline of knobs. You can imagine whether you're going to be tempted to start to fiddle to get some nice results. So we have seen that. And we've also seen that if you resist the urge to do that, these graphs get bad in ways like these graphs. So it would be an oversimplification to say that the result I'll be talking would apply to both cases. And in fact, it would be an oversimplification to say that any particular set of graphs, including the ones I'm going to be showing you, follow exactly the sort of nice story I'll be describing. So we've looked at 180, 200 graphs that fall into a couple categories. Everyone's going to be an exception to a nice, simple story, but I'll try and lay sort of the high-level ideas here. So you think of technological graphs, biological graphs, social graphs, information graphs. So any graph you have would probably fall under this sort of umbrella, modulo the details of saying whether you can engineer it to be nice or not. And people think about time-directed graphs, time-varying graphs, directed graphs, graphs with meta information on nodes and edges, lots of bells and whistles. So for today, I'm just going to talk about the simplest thing, the interaction graph model of networks. So the nodes represent things, edges will represent pairwise interactions between things. You can weight the edges, everything goes through. Directedness introduces some subtlety, time varying, all these sorts of things introduce a lot of subtleties. And it's actually hard to make claims about, if you want to develop methods or you just want to make a downstream claim, fine. But if you want to develop methods that are sort of particularly well suited for downstream applications, it's actually hard to do that with, say, time varying graphs. And the reason is there's just not a lot of high-quality graphs out there that are time-varying where you have very reliable information on the nodes and edges and so on. I'm talking about graphs more than 5 or 10,000 nodes. When you get below 5 or 10,000, it's easy to engineer a lot of domain-specific stuff that's not going to be general, and they're sort of small when you get below about 1,000. So, with that caveat. So, and I say that because when we started this, we looked at 80 or 85 different types of graphs, and really every one was an exception to simple rule. I mean, if you had given me any 1 or 2 or 10 or whatever of those, we couldn't have made the claims we made because basically each graph was sufficiently noisy and messy that it was not clear what was going on. We had to sort of draw strength across all of them. And I think to make the next sort of step to looking at time-varying graphs, you would need a corpus of dozens at least of graphs to play the graphs against each other, to play the algorithms against each other, and in order to be confident that what we're seeing. So I'm not going to talk about that stuff today. Okay, so this is what graphs look like. So graphs, so you probably, if you know anything about networks, you've probably seen a hairball like this, just a sort of mess. This visualization algorithm, so if you know the state of the art in visualization algorithms, you'd probably be able to tell me which visualization algorithm we use to visualize that. If you know the state of the art in graph analysis, you would not be able to tell me the publicly available graph that we're visualizing there. So these visualization algorithms, when you get beyond 1,000 nodes, whatever, reveal sort of more about the inner workings of the visualization algorithm than they do about the graph in most cases. So that's not so good, but it suggests, maybe, if the graph looks like this, it's some hairball that you can't visualize. use the visualization algorithm sort of as an experimental probe of the graph. More generally, can we use approximation algorithms as experimental probes of the graph? Think of the graph like a protein or something. You can't analyze it, but you can send in X-rays and NMR and do stuff like that. So poke and probe at the graph with different approximation algorithms and trying to understand what you observe, not in a sense from some worst-case bound of the approximation, but as a function of the geometric or other sort of statistical peculiarities of the approximation algorithms. So that's going to be the connection with the network stuff I'll talk about in the implicit regularization. So take a step back and sort of think at a high level, what are possible ways that a graph might look? So one way a graph might look is, this is a grayscale, and there's a bunch of nodes that talk to each other and a bunch of nodes that talk to each other and less crosstalk. So this is a very intuitive thing, right? You have two clusters, they talk to each other quite a bit, less crosstalk. It could be the case, if you think of this as sort of 4 blocks, that there's one cluster that talks to each other a lot. There's one cluster that barely talks to itself. Call it a cluster, but we'll call it whatever. And then the interaction between those two sets is intermediate. It's certainly possible, right? It could be the case that it's all gray, and whether it's dark or light gray depends on parameters you fiddle, but there's no good clusters of any size. They're all about the same. And you can have bipartite and lots of other structures, right? So this is probably the most intuitive, and you can imagine that a lot of algorithmic and statistical techniques think about the data this way, because you can cut it in half in a recurse. And it's an empirical question. I mean, maybe the data look like this, and maybe it looks like that, and who knows. Now, it's not clear how you'd answer that question, because this is sort of an idealization, but you can at least imagine it. Let me skip that and say that the way we're going to ask this question is we're going to use a combinatorial notion called conductance. If you're familiar with machine learning, think of normalized cuts. So this is, it's a surface area to volume notion. It has very sort of close connections with spectral methods and a range of other methods. And it's under the hood in a lot of sort of algorithmic and statistical techniques in ways that I'll mention. So let me define this and then say sort of why it arises. So I have a graph, a bunch of nodes and a bunch of edges. Don't think about any niceness. Let's say the conductance of a set S is a set of nodes, the subset of the vertices, is phi of S is the sum of I and S, J and S bar of the adjacency matrix from Aij. Forget about weights. It's the sum of the edges between the two sets. It's a surface area. If an edge is crossed between two sets, it's a surface area. Divided by a volume. You can put different volumes down here. The fact that it's a min, don't worry about. It's a volume notion. It's the size of S. It's the number of nodes or edges in S. So this thing is intractable to compute. It's NP hard. The thing I skipped over in the last slide was a second eigenvalue. If you're familiar with that, spectral methods get second eigenvalues, and they approximate this, but they approximate it in a weak sense, but in a good sense. So this is intractable to compute. So I'm going to ask, but it's a surface area to volume notion. And so here, you might say, the best clusters are 50-50, right? There's a left half and a right half, and I want to recurse. Here, it's not clear that that's the case, right? They're all bad. Here, who knows what's going on. So rather than asking for the best cluster in the graph, which is a very common thing, and spectral methods do that, and a lot of Eigenvector methods do that, what I want to ask is a size-resolved version of that question. The network community profile plot, we're calling it that for historical reasons, is the minimum over subsets of the vertex set of size k, of the conductance of that set. All right? So just as conductance captures a surface area to volume, this NCP captures a size-resolved surface area to volume. It captures, because conductance is related to diffusions with spectral methods, a size-resolved notion of bottlenecks to random walks or diffusions. So this seems, if you haven't seen this before, this may seem esoteric. This should be as sort of familiar as the back of your hand, if I describe it not in such an esoteric way. So it's a size-resolved version of isoperimetry, of surface area to volume, right? So I'm going to show you a bunch of plots. Down is going to be good. So think of yourself, you have a hot dog. Or a pancake, it just is a hot dog that has two axes that are the same. Are the best clusters in this hot dog 50-50 or 99-1? Isoperimetry. What are the best surface area to volume sets? Isoperimetry says the best set is a circle, best in the sense of surface area to volume. What I'm asking is a slightly more refined version of that. I have a hot dog, and what is the best way to cut this hot dog in half in terms of surface area to volume? And it's right down the middle. meaning that if I look at a size-resolved version of this, the best anywhere in that plot better be 50-50. If the graph is a random graph that has no good clusters or anything, you might imagine there's no good clusters anywhere because isoperimetry is bad, and maybe there's other possibilities. So why worry about both criteria, surface area and volume? So for some graphs, namely the graphs that are informing your intuition, hot dogs and pancakes and road networks and things that are low dimensional, finite element meshes, namely things scientific computers do, compute road networks, cut quality and cut balance work together. So down is good. As I go to larger graphs, bigger circles are better than smaller circles. Circles are better than triangles, but they both go down. And so if I ask for the best cut in a graph that sort of lives on the Earth, this is going to go down. And it's going to be an empirical question to say, how does it behave in real graphs? And this is a forward-looking pointer. But now, this is intractable to compute. We want to make an applied claim. So just to give you sort of look under the sheets a little bit and say, how are we going to make this claim? So the lay of the land in terms of approximating partitions is that there's spectral methods that compute an eigenvector, an exact or approximate eigenvector, and use that to cut the graph. You get Cheeger's inequality type guarantees. Cheeger's formulated in a continuous place with analogs and graphs, which gives you a quadratically good approximation. There are graphs that are that bad. They're sort of graphs that have a clump with stringy things hanging off. I won't define more detail. That's what statisticians would use. That's what machine learners would use. That's what scientific computing people would use. That's what mathematicians would use. You could say, geez, the conductance, I can write it as an integer program. I can relax that integer program, use multi-commodity flow, the all pairs multi-commodity flow. This gives me a log n approximation to that intractable objective. These two things are completely different. They're incomparable. And so what we did is to say, and the log n is achieved. It's achieved on expanders, where expanders are graphs that do not have good partitions. So real graphs have expander-like properties. They have long stringy things. They're sparse enough. If you have 1 million nodes, you have 10 million edges things. So you're obscenely sparse. So we're going to use spectral methods. We're going to use flow-based methods. We're going to use a lot of smart heuristics and a range of other things. And we're going to take this hairball and we're going to poke at it and probe at it. And we're going to try and understand what this thing looks like based on knowledge of the implicit embedding, the mathematical, the statistical properties that these scalable algorithms have in them. So we want to use theoretically principled things to tear the graph apart. But also what we're measuring is a property of the graph, but also a property of the method that we're tearing the graph apart with. So we want to use spectral and flow and play them against each other. And in fact, we don't want to use it with one graph. We did it with 80 graphs and now more than. Okay, so this is what this size-resolved isoperimetry looks like. If you're on a one-dimensional chain or two-dimensional grid or anything, it goes down. The slope depends on the dimensions. So if you're in 100 dimensions, it's going to be essentially flat, but it goes down in principle. Anything that the qualitative property of going down is very robust. This is an extremal metric, so extremal metrics aren't robust, but the qualitative property of going down is very robust. Road networks, anything that lives on the Earth goes down. If you use small networks like this or this that are nice to visualize, namely if you're reading a paper that has a nice network that you can visualize it because it sits on a two-dimensional piece of paper. That means you can cut it in half. These plots will go down. So how do real data look? I'll show you a couple more plots in a minute. But this is about the smallest graph that we could illustrate the method on. It's about 4,000 nodes. It's actually a rather small graph. The plot goes down and down until you hit about 20 nodes, and then it goes up and up and up and up. So you have good small clusters that look like that. Aside from that, they're all bad. And they get worse and worse. And sort of intuitively, what's going on here? So I could show you 80 other plots. I'll show you a few more in a couple minutes. But the idea is that you have good small clusters, and the best get worse and worse and worse. So I'll tell you how we got that with the regularization and the eigenvector localization, but take this as given. The interpretation in terms of the graph is that there's a core and a periphery. So remember I showed you there's a bunch of nodes that talk to each other, a bunch of nodes that don't. And the intermediate nodes, there's some intermediate level of granularity. So think of the graph as a bunch of whiskers. Whiskers are small things that you can cut off by removing one or two edges. You're going to want to say those are nuisances. Right? Cut them off, and now you deal with the real part of the data set. So 20% of the edges and 40% of the nodes are whiskers. There's a big variance on that number, but over the corpus of 80 graphs, huge fraction. If you cut those whiskers off, you can ask, how does that plot change? That plot went down. Do I have it on the next page or not? I don't. That plot went down and then went up. If you cut all those whiskers off, the plot's unchanged. It shifts just slightly. Why? Because if you define the core to be the rest of the graph, the other 60, 80, Now you also have core periphery structure. We have whiskers that are now connected by 2 edges or 3 edges or 4 edges, and you can recurse that each time you're pulling a constant fraction of the nodes and edges. And you don't need to do that many times before you remove 99% of the graph. So you should think of these whiskers as not nuisances, but real things in the data. Now they're nuisances by classical statistical techniques because it's a fluctuational effect in a sense. But if you are in a social graph and you want to know about what's going on in that social graph, you want to know about you and your 100 friends. So that dip you should think of as something having to do with the structure of you and your 100 friends, but you and your 1,000 friends, or you and your 10,000 or 100,000, or you and your 7 billion closest friends, this is going to get worse and worse. All right? It also means, remember, this is a log scale. If you do recursive partitioning with spectral partitioning, you're cutting off 20 nodes out of 4,000. That's not so bad if it's 4,000, but you see the same 20. It might go up to 40 or 30 or something, but you see the same 20 if you have 4 million or 100 million. So that's a little bit worse. So that's a real effect. What's the simplest possible model that will reproduce this? So take this as a fact. I'll describe some more recent results that will show an example where this breaks down, but a huge fraction of social graphs, information graphs out there, have some number of nodes, say 1 million, some number of edges, say 10 million or 5 million, not more than 10 or 15. So obscenely sparse. And in those, you have small clusters that are good by this measure, which is a reasonable notion of clustering, but it's also related to algorithms. You run spectral algorithms. This is a cluster you'd find. What's the simplest possible model that will give you small clusters and no good large clusters? So a model that would give you good large clusters and no good small clusters is like a random geometric graph on the line or the plane. Just for the isoperimetry reasons, right? A model that would give you no good clusters of any size is a random graph, like an Erdős-Rényi random graph, if you choose the parameter p, the connection probability, to be not obscenely sparse. To get a dip in this plot that's small and no good dips that are large, Erdős-Rényi will do that for you. If you choose the connection probability to be 3 over n, or 5 over n, million nodes, 5 edges on average. All right? Randomness and obscene, incredible sparsity. So noise, extremely sparse, you get a fluctuational effect. Of course, if you're most interested in you and your 100 friends, this isn't a fluctuational effect. This is all that matters. You don't care about what's going on with Britney Spears or someone that has 1 million followers on Twitter. You care about what's going on with you. So this is an outlier by classical statistical algorithmic techniques, but it's the thing that's most interesting for you in the data. So you should think of the data as sort of local structure, you and your 100 friends, and you and your 100 friends, and you and your 100 friends. Now, if you and your 100 friends linked to people in ways that are incredibly strongly correlated with the way each of those people link to their friends, and each of those people link to their friends, and each of those people link to their friends, none of this would matter. But basically, if you inject any noise, and 3 hops down, they link to some random person, what random means essentially not perfectly well correlated with the data generation mechanism. So it's a fairly weak notion of random. Think of the data as little local pockets of structure on some global noise. And that's actually a real challenge for a lot of algorithmic techniques and statistical techniques. And this is where we're going to see our eigenvector localization. So before I get to that, just a few more pretty pictures. So we looked, so this was what we knew 2008-9 time frame. A couple of years ago, we went back and looked at a broader class of graphs, which included a bunch of the Facebook, about 100 graphs from Facebook from the early days. This was released and unreleased at some point. And so at that time, we were able to look at it. And so think of now 3 different types of graphs. One, the graphs I was telling you about, 1 million nodes, 5 or 10 million edges on average. The point about a lot of the graphs that are generated in Facebook and a lot of other social networks is you don't have 5 friends on average. You may have 50 friends. And once you have 50 friends, they try and get you to add more friends. And maybe you're more popular than me, right? But it's hard to keep track of 50 friends. And so when they say, maybe you should link to this 51st person, this 52nd person, this 53rd person, and the 152nd person, the semantic meaning of that edge is probably less significant than the first link, which is probably to your spouse, your children, or your parents or something, right? So they're essentially injecting noise into the graph, qua graph. Now, they're doing it because they don't care about the graph structure. They care about the meta information and all the stuff that goes along with it. But qua graph structure, so now you have a graph, 1 million nodes with 100 million edges on average, which is essentially like the ones I was talking about before, but with a lot more, quote, random edges. And you see exactly the same thing as you did with Erdős-Rényi if you put in a bunch more random edges. Namely, things get homogenized more. There's still some structure in there, but it's going to be harder to identify. So I'm not going to go into full detail about that, but using some fancier versions of the local spectral things I'll get to in a few minutes, we're able to tease some of that stuff out. So the three graphs are the stuff I've been talking about. Some Facebook graphs, nothing special about Facebook, could be other things. You just are interested in harvesting the meta information. You inject a lot of extra edges in for that reason. And I'm calling this US Senate. Basically, it's a voting pattern of the US Congress. There's a link if people voted together. A given senator links to himself or herself and the two adjacent Congresses. The point here is that a senator can't vote with a senator from 100 years ago because they weren't alive together. So this is a time series. There's a natural one-dimensional ordering. This is a hot dog. Now, it doesn't look like a hot dog, but that's because I used a two-dimensional force layout here. If I had used a one-dimensional or three-dimensional layout, I'd see at least as much about the visualization algorithms as about the graph. But this, you can believe that if I used a two-dimensional force layout and I tried to lay out a hot dog, it would get bent around a little bit, and you'd see exactly this. So the point is there's nice clusters here. And you can imagine if I have a bunch of labels here and a bunch of labels here, and I want to make some prediction. And I want to predict, given that you and you and you like something, will one hot neighbor like that. There's a lot of redundancy here, right? If I have a bunch of positive labels there, I'm going to have algorithmic control to cut this thing up, but I'm also going to have statistical control, right? Because I'll be able to make a prediction here. I might not be able to make a reliable prediction about here, but if I have a bunch of labels there, I can make a prediction, right? This is at the heart of a lot of statistical techniques. And that's a natural assumption, right? You go to some limit, you get some redundancy, you get something like this. If you're in the situation we had before, how am I might be able to make some prediction in here, but I have just one or two edges. As soon as I leak a little bit of information out here, boom, I'm going to touch the whole graph. And the reason I'm going to touch the whole graph is that there's a reasonable cluster of size 50, but if I want the best cluster of size 100 or 1,000, I quickly touch the whole graph. Now, you might say, geez, I don't care about clusters and communities, and that's a fair point. Or this isn't the right notion of clusters or communities, and that's a fair point too. But the point is that if you want to make inferential claims typically come because you're thinking about the data in a low-dimensional space, and you're thinking about the data has a left half and a right half, and if I have a bunch of pluses here and a bunch of minuses here, then more likely than not, if I have a new point here, it's a plus, and more likely than not, if I have a new point here, it's a minus. Whereas if everyone overlaps with each other pretty strongly, they have strong expander-like properties, everyone's going to be a one or two hop neighbor from everyone else, and so you don't have that control that gives you good inference. And so we've looked at a bunch of other sort of things that are related to that. All right, so regularized and non-regularized communities, and this will get us to local spectral. So this is actually, I think this plot more than any of the plots. And the reason is when we saw this and really understood this, we knew we had gotten something significant. So I told you we're solving something intractable. We're poking at these graphs. We're tearing it apart. To justify that, I'd have to spend 3 hours describing what we did. So think of it as like an experimental protocol. You see the nice pretty picture at the end of the day of the protein, but you don't know the whole protocol that went into the crystallography underneath it. So I showed you the pretty picture. The plot goes up, the plot goes down. Take one step before that. How do we do that? So we did spectral flow, tore it apart this way, that way, and we got a scatter plot of a bunch of things, and we took the min of the scatter plot. So here's the one step before we took the min. So x-axis is size, y-axis is the cluster quality. Down is good. So red is a flow-based method. Blue is a spectral-based method. So you don't need to know what spectral and flow are, except to know that they're two different methods. They come with strong theoretical guarantees. Computers to oversimplify. Computer scientists like one, everyone else likes another. If you believe that conductance was the objective you cared about, and I said before, maybe you don't, or maybe you think, if you believe that conductance was the objective you cared about, down is good. Say I went interested in clusters of size 1,000. No question here, right? Red is better than blue. Period. Shouldn't even touch spectral. We give the downstream people that gave us the graphs, the ones we said just generate them your way and we'll tear it apart, both clusters, and they said, well, geez, the blue clusters are clearly better than the red clusters. There's a bit of garbage here, so ignore that, but those blue clusters, clearly better than red. Why? Okay, so they had some stories to tell. We asked them to quantify something. Look at the diameter of the cluster. You might say a cluster is nicer if it's more compact. You might say a cluster is nicer if it's not two clusters that are weakly connected. So come up with a few metrics like that characterize how nice or round it is. And blue, down is good on these two plots. Blue is clearly better than red. Blue is clearly better than red. And again, there's a bunch of garbage here, so that blue is clearly better than red. All right? So what I have here is an objective. Red is better than blue, and I have two different niceness measures. Blue is better than red. So what is this thing? What is this an example of? 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 What is this So this is an example of regularization. All right, regularization is not write down Bayesian priors. It's not write down f plus lambda g's for some regularization parameter lambda. It's not Tikhonov. It's not truncate singularity. It's not none of this. Regularization at its heart is a trade-off between solution quality and solution niceness. If the problem's not well posed, then you're going to be wildly sensitive to something. And so what you do is you introduce some bias or you do something, which means that on the objective of purported interest, you're worse, but you're nicer, you're more round, you're more robust, you're more smooth, so that tomorrow when I see data, I get a better answer. So here, this is, typically it's formulated for vectors, data points in Hilbert spaces and Euclidean spaces. There's no Hilbert spaces here, right? These are graphs, and I ran two different approximation algorithms for the same intractable objective. And what we're seeing here is the defining feature of regularization. And the reason is that spectral methods take this intractable thing and embed you one way. Flow-based methods take this intractable thing and embed you in a very different way. And there's a bunch of trade-offs here. So in the last bit, I want to talk a little bit about the localization. I'm not going to talk about the flow stuff as much. I can talk offline if anyone's interested in that. But I'd like to talk about how we got this sort of spectrally. But how we got that and understanding the implicit regularization, the eigenvector localization, is basically understanding the geometry implicit in these approximation algorithms. So you can write down an objective and go to some nice asymptotic limit and say this objective captures something. Or you can just say run algorithms on data, solve some problem, and ask what is the problem I solved. And the problem you solved probably bears some resemblance to that, but it's certainly not exactly that. And in some cases, there's interesting statistics and computer science and mathematics to be found there. Okay, so local global properties of many data, just empirical data, are very, very different. I didn't talk about the graph construction, but if you construct graphs and you don't overly homogenize it, you see very similar results. Local spectral methods are the big winner. I'll say what I mean what local spectral methods are. Little design decisions make a big difference. What you want to say is, all these types of diffusions, all these random walks, all these things are about the same, so I'm going to use whichever one's most convenient given what I know. And that's true if design decisions are second order. But in a lot of these cases, the surface area to volume is very bad, and other properties are very bad. These second order effects really are first order. And so little details make a big, big difference. An approximation algorithm, if you're a computer scientist, the usefulness of approximation algorithms is largely uncoupled from what the worst case theory suggests. And it's because you want to get worst case bounds. The approximation algorithms embed the data in a metric space, typically an L1 type metric space, for instance. And you're most sensitive to the farthest away data points. And so that's actually a real challenge to get better algorithmic methods where that coupling is close. So that's true much more generally, I think, than what I'm talking about here. So let me talk about eigenvector localization and sort of a little bit more of what's going on under the hood, but pause for a second, because one of the main things, aside from the sort of general ideas, is just like conveying some results on what real large, meaning I showed you the smallest I could possibly show you, 4,000, but up to 100 million. When you get larger than that, you need to deal with data management issues, but similar results hold. But large graphs look like. And they look like they have small pockets of structure, but no large-scale structure. And that's a real challenge for methods like spectral methods that eigenvectors are global things, right? You're optimizing a global objective. Flows are global in a different way. So real challenge for algorithmic and statistical techniques, the way they're typically formulated. All right, so the idea of these methods, so spectral methods in graph theory are basically the following. I have a graph. It's a combinatorial thing. I construct matrices from the graph. It could be an adjacency matrix and Laplacian, and there's better and worse ways to do that, but I construct a matrix from the graph, and I compute eigenvectors of that matrix. And, for example, if I take the leading non-trivial eigenvector of the adjacency matrix or Laplacian and put all the nodes on that, meaning I use that as an embedding. So I have the eigenvector is a function over nodes, right? Because it's a vector in Rn, where n is the number of nodes. So if I view that as an embedding of the data, then I can, if I normalize things, the values are between 1 and -1 or whatever, I can order the nodes from -1 to 1. I can march from the left to the right. And I look at n different partitions that defines. And if I look at those n different partitions, as opposed to the 2 to the n, that's the intractable thing, I get a partition that is quadratically good in the sense of Cheeger's inequality. So that is the spectral partitioning algorithm. Alternatively, I could say, listen, why don't I run a random walk on the graph? Because I know that if I run a random walk forever, I get the leading non-trivial eigenvector. exactly, so there's machine precision issues and whatever. But I get the leading non-trivial eigenvector. You can do that. Now, if the leading non-trivial eigenvector, as most of you probably know, if there's no nice spectral gap, the second and third eigenvector are very close, you're going to have rotational issues. You might swing 90 degrees. And so in that case, all this theory is robust. Any vector in that space has a Rayleigh quotient that's approximately optimal, and so you'll get a good partition. The actual partition will be very different, but the objective function value of that will be similar. So local spectral methods take the idea, the random walk version of that, and say, I'm not going to run 1,000,000 steps, or I'm not going to run 100 steps, which I'm thinking of as approximating 1,000,000. I'm going to run 3 steps. I'm going to run a small number of steps. And my initial node is not going to be uniformly distributed over on the graph. My initial node that has my mass is going to be localized here, right here. And if I take 3 steps of something localized here, I'm not even going to see the other side of the graph. And so the intuition is, because spectral methods will have, triangles will close and you might walk back on yourself. If you're at the small side of a small cluster, you might find it if you're on 3 steps. And otherwise, you'll touch a large number of nodes and you can certify that you're not in a small cluster. Theorem, you're going to get local Cheeger-like guarantees that are locally biased. So that's what a lot of the stuff in spectral methods have been used. So Spielman-Tang used truncated local random walks. They were interested in nearly linear time solvers for linear equations with Laplacian constraint matrices. ACL, Anderson-Chung Lang, used a spectral ranking called PageRank version to do this. This is the one we'll use. This is actually a very nice one. Chung used heat kernels. There's been other ones since then. And the idea is, rather than starting a random walk somewhere and running 1,000,000 steps, in which case you partition the US along the Mississippi and get something that's 50-50, if I start here and run 3 steps, I might just get a small cluster, locally biased around me. I might nibble off Florida or something. And I should be robust, right? Because it doesn't matter what goes on in California. If I never even see it, by definition, I have to be robust to it. So can you make that precise? In addition, if you want to find a small cluster, you'd ideally like not to touch the whole graph. If the whole graph's 4,000 nodes, that's not a problem because you can run cubic time computations or whatever you want. But if the whole graph's 4,000,000 nodes, that's a different thing. So I'd like to, if I want to find a cluster of 100, I'd like to run in 1,000 or 10,000 time, not 1,000,000 time. So spectral graph partitioning. So if you've seen this stuff before, this is just to set the letters so that you know what I'll be talking about. If you haven't seen it before, I'll sort of point out what's essential, but don't worry about what most of the letters mean. But the point is, if you run spectral partitioning, you can compute an eigenvector, run a random walk, do an operational thing, or you can view it from the perspective of optimization. And the basic optimization problem is minimize this quadratic form, a Rayleigh quotient type form, subject to being normalized in a certain way and avoiding the trivial eigenvector. And if you know what that means, good. And if not, don't worry about it. You're optimizing this function. This isn't convex because of those constraints. So how is it solvable? If you're a convex optimization person, you probably say convex things are good and not otherwise. The reason is this is sort of convex in a different place. We'll get to that. But it's an eigenvector problem. So this objective is a relaxation of this thing. This thing is what we saw before. Surface area, number of edges between S and S bar, divided by volume. This is an integer program. It's an intractable discrete thing. If you relax it in a certain way, you get this. This is solvable as an eigenvalue problem. You get a vector, and you do a sweep cut, and you get a number, lambda 2, the second eigenvalue, that is close to this intractable number, in the sense that on one side you're bounded by a factor of 2, and the other side by that factor of a square root. That's Cheeger's guarantee. So this holds more generally, but this is the case when you get the limit case. So to get local spectral methods, you have to use a version of Cheeger's inequality from Mahoney that works with any test vector. So we want to take the idea that if you start here and run a random walk, you're going to find a good cluster if it's near you. So that's what Spielman-Tang and Anderson-Chung Lang and these methods do. That's what we actually used in tearing apart the social graphs when I said we use spectral methods. Can we understand what's going on? Because it's not exactly clear. Can you take an optimization perspective and maybe understand the regularization properties there? So to do that, let's, given a cut, which is a bunch of nodes, let's define a vector. This looks complicated. It's essentially the indicator vector of that partition, of that cut. Since I need to stay off of that trivial eigenvector, it's a little more complicated. That's an indicator vector. I use that to define a notion of correlation. So I have a combinatorial graph, and I'm defining, sort of imposing a geometry on it, a geometric notion of correlation. The indicator vector dotted into the ones vector is 0. The indicator vector dotted itself is normalized. The indicator vector is a correlation vector. So it's a reasonable notion of correlation. It's the first one you'd think about. If you used another one, you'd get a different random walk, but it's the first one you'd think about. And let's say, given a graph and a number between negative infinity and positive lambda 2, the second eigenvalue of your Laplacian, a generalized, personalized PageRank vector, GPPR, is a vector of this form. So who knows who's heard of PageRank vectors? 3 people, 4, 5, 6. Okay, so it's some non-negligible fraction. So PageRank was popularized because Google used it in its early days. It's a way to perform something called spectral ranking. I have a graph, and I want to sort of iteratively determine what something is important. One way is the degree. If I have a high degree, I'm important. You can spam that, literally in the sense of spamming. And so, you might want to say I'm important if important people link to me. So now I've done an iterative thing. And if you do that 2 or 3 times, you're going to get eigenvectors. And you need a damping factor because, there's something lost in the fact that, if you're important, you might link to other people. So you introduce a fudge factor. There's a bunch of things that go by the name X-rank, and one of them is PageRank. But a lot of spectral ranking methods boil down to that. Sometimes that's described in terms of a drunken random walker. You have a graph. I start here. I diffuse around with probability point whatever, and with some probability 1 minus that, I jump anywhere in the graph. And that's the way it's usually formulated. And that gives you a ranking over the whole graph. You could say, geez, I'm interested in not the ranking of this thing in the whole graph, but you might be particularly interested in, say, the flower market in Lyon as opposed to the flower market anywhere in the world. Right? You can imagine people are interested in that sort of thing. I want to provide a personalized ranking or a locally biased ranking. So how do you do that? Take your same random walker, he random walks around, and he always jumps back to a seed set of nodes in Lyon. Right? Say I want to find you and your 100 friends on Facebook. I jump back to you. It's a personalized notion of ranking. So that's the usual PageRank. So if you've seen PageRank, you might not recognize this as a PageRank vector, but it is. It's generalized in the sense that if you jump around and you teleport around, the probability that you teleport around corresponds exactly to this parameter when you go between negative infinity and 0. Meaning you can implement PageRank for a subset of the possible values of that parameter with a random walk. Alternatively, you can write it as a linear equation. This is the Laplacian of the complete graph minus something I'll get to in a second, pseudo-inverted times d, ignore d, times a seed set S, which is a linear equation. So you can solve this as a linear equation. This is generalized. And this allows you to solve it all the way up to positive lambda 2. Now, what is this thing? Because this is regularization. I told you the drunken random walker, and he teleports back to the seed set. That's a way to implement regularization. Why is that? So basically, I'm saying I have my vector. I take the inverse of the Laplacian. Ignore this thing. I take the inverse of the Laplacian. D, just scale stuff. Ignore D's. Times a seed set. So the seed set here is on a small number of nodes. Pseudo-inverse of the Laplacian says, take the pseudo-inverse of the Laplacian, take those small number of nodes, dot into those rows, you get something. Right? And that something disperses information or stays localized depending on whether the graph has local structure around here, and that's encoded in the pseudo-inverse of the Laplacian, because that's the inverse of a correlation matrix. That encodes information about the random walk. So that's if I just had L and ignored that. What if I have that? So you might be familiar in PageRank, you have Laplacian minus parameter times D, a diagonal degree matrix. As a technical matter, the diagonal degree matrix, if you force yourself to stay off of the rank 1 space, that is the Laplacian of a complete graph. If you don't understand that, don't worry about it. But the point is that if you implement this algorithm, that's a start here, run a random walk, occasionally teleport back to a seed node, what you are doing is solving for this. Pseudo-inverse of the Laplacian minus a parameter times the Laplacian of the complete graph. What you're saying is I'm going to diffuse around, and I'm not going to totally pay attention to the graph. I'm going to pay a little bit of attention to something else, where the something else is uniform over everywhere in the graph. That's a way to engineer a prior, essentially, into this algorithm. So this is a form of regularization there. So what can we show about local spectral partitioning? So you have the primal problem, X transpose LX. So this is an ansatz. I'm pulling this out of the air. Minimize x transpose Lx such that x transpose x is 1, and I want my vector to be kappa correlated with the seed set S. I want it to be well correlated with the seed set. The interpretation is I want to find cuts that are well correlated with the seed vector. If I want to find clusters around U, I want the partition to be near U. Maybe there's a good partition on the other side of the world, but I want that prior that I engineered in to ignore that, and I want it to be biased towards U. If S is a single node, here's an intractable combinatorial problem that's locally biased. Find this best subset of nodes that contain S that's of size less than 1 over K. That's not too large. Here's an intractable thing, relax it, you get this. Not clear we solved anything because this is not convex and it's messy. Theorem, if x star is the optimal solution to that ansatz, it is of the form of a GPPR vector. Namely, you can solve it with a linear equation solver for some parameter f, so it's a set of linear equations. There's a proof that we had to go through an SDP and show that there was zero duality gap there that I'm going to gloss over. So the proof's interesting, but the bottom line is you can solve this purportedly intractable thing just because of the structure of the constraint, and you can solve it as a linear equation. Theorem, you get Cheeger-like guarantees. I'm not going to go into the quantification, but in the same way as the global spectral partitioning is good in a certain sense, the local one is good also. The idea is if I put my seed node here, I'm going to get red, I'm going to get orange, I'm going to get light orange, and I'm going to get yellow. I can go find the global partition if I choose my parameters to get yellow, but I can find local clusters here. And if I'm more centrally located like this guy versus less centrally located like this guy, as I sweep over the parameters, red to dark orange to light orange to yellow, I'll explore different parts of the graph. Seed vector could be more general. Sort of visually, we're doing this with a social graph. This is sort of a standard computer thing. You have a tiger or something in the middle of the woods. You have a sky. You have land. You have a tree. You have a lake. You have lots of stuff in your image. Partition this image. And normalized cuts takes this, cuts it in half. And if you know anything about computer vision, you've probably seen a picture where they cut the sky in half. They cut the sky off. You'd never find this tiger with using global eigenvectors. But if you put 1 or 2 seed vectors here and solve that locally biased version of spectral partitioning with linear equation, or if you ran a local random walk starting at those seed nodes, like the ACL method, you pull out the tiger. This is sort of a pretty picture illustrating what we did before. You can get a bunch of other vectors and extend these to kernel methods if you want. So let me, what's the time to wrap up now, or a few minutes, or I don't know when we started actually. Okay. So the idea is if you run 1,000,000 steps of a random walk, you get the global eigenvectors. Eigenvectors are global things in the sense that they optimize an objective. But it's a little bit awkward, right? If you have a very small cluster here, a very small cluster here, a very small cluster here, the requirement of exact orthogonality is a little bit awkward because in the Florida example, you don't necessarily want to be sensitive to what's going on the other side of the world. And eigenvectors are. I can have a graph that's, expander-like, a cluster here with some number of edges, a cluster here with some number of edges, and I can be the best eigenvector in the entire graph, and I change one edge somewhere, and I swing, and this is the best eigenvector in the entire graph, and this has no weight now, essentially no weight. Now that is two things. It's one, the usual 90-degree rotational degeneracy of eigenvectors, but even worse, you've changed where the eigenvector mass is, and that's awkward because if you start your mass here and you run a diffusion or iterative algorithm, it just takes a long time to get that mass to some other part of the graph. So there's a question of sort of which direction is the vector pointing in, but there's also the question about where's the mass located. And these things are sensitive to that in a very strong sense. So what I said is you can start here with a random walk. PageRank was one version of it. The heat kernel was another. The lazy the random walk where you truncate small entries to 0 is another. And you get local spectral methods, and that's been useful for a lot of different things. I also gave you an objective function that is the usual global spectral objective with a locality constraint tacked on. I showed that the solution to that is a linear, is a generalized, personalized PageRank vector that just because of the structural form of it, pseudo-inverse of the Laplacian times a seed vector, that's the usual form, no regularization, you get the exact solution to that. Pseudo-inverse of the Laplacian plus parameter times some dumb null model that is essentially the Laplacian of the complete graph, pseudo-inverted times the seed vector. That's a way to engineer in regularization. So I'm going to show you 2 of the slides, skip over a bunch, but show you 2 slides to sort of close the gap and to say, sort of instead of a richer way, how do we want to engineer in the localization? So say I am running a random walk. What we've said is that if you run 1,000,000 steps of an iteration, you get the second eigenvector. What if you run 10 steps of an iteration, or 20, or 30, or 40? So if you start with a seed vector that's pretty delocalized, you might approximate that. If you start with a seed vector that's very localized, you might find one of these local clusters. Can we say something more generally? What does an early stopped iteration do? And the second thing is, what's the difference between the ACL method where you diffuse a bit and you truncate small things to zero and that objective I put down? One is that the objective I put down, if I'm interested in what's going on here in the graph, it actually touches the rest of the world. And I might want to not even touch the rest of the world because I can engineer in robustness and stability that way, and because I don't have to touch the whole graph, which is a good thing if you have a graph with 100 million nodes. So the usual way to think about regularization is f plus lambda g. So can we write what we've been talking about as f plus lambda g? So different random walks you can write as operators. These are the operators, H, R, W. It's a big matrix. You can write it down as an operator. I wouldn't suggest you implement it that way, but if you run different random walks, you're iterating different things, and different operators sum over paths of different lengths in different ways. So here's the objective we had before. Here's the SDP we had before. Here's regularization on the SDP. Theorem that's sort of easy to show. Corollaries, do I have that? Okay, so what I want to say is I have F plus lambda G, which to confuse you, I'm calling F. F plus lambda G. All right? If you run 1,000,000 steps of any of those random walks, you exactly optimize this. If you run a few steps of any of those random walks, you optimize this plus lambda this, where the regularization term is either the generalized entropy, that gives you the heat kernel matrix with T depending on that value of lambda, or a log determinant. If you use a log determinant, you get that page rank, exactly the thing I was talking about, with T depending on the regularization parameter. That's related to the teleportation parameter. Or a certain matrix P norm gives you the truncated lazy random walk. So if you run 50 or 100 steps of any of these diffusions, theorem, you approximate the Rayleigh quotient, the 1,000,000 steps, insofar as the spectrum decays. So it's a legitimate approximation algorithm. Theorem prime, you exactly solve a regularized version of the problem, in the sense that I'm optimizing objective plus lambda regularization function. And the regularization functions are generalized entropies, heat kernels, log determinants, things like this that they should be familiar with. So random walks are a robust notion of eigenvectors in this sense. And that's used a lot of when the eigenvector localization was useful or not is because we're implementing regularization inside the algorithm. The ACL method, you may believe that if you're running these random walks, this is all inside the analysis. You might believe that if you're running random walks, you're optimizing this. So here's the equation I had before written in a different way, but that's exactly the equation I had before. Minimizing edge incidence matrix with a 2-norm penalty. Least squares regression. So don't worry about all the letters are because I skipped over that. You're solving an overconstrained least squares problems with 2 things nailed down. So if I run the page rank diffusion, set the parameters right, I'm implicitly solving, in addition to the things I was talking about before, this least squares problem. What if I run the version where I truncate small things to 0? Where, as I said, is of interest for 2 reasons. One is you don't have to touch the whole graph. I can find clusters of size 1,000 in 10,000 time. It's also the case that I exactly solve objective plus regularization parameter times a 1 norm. So before I had an L2 objective with a vanilla diffusion, non-vanilla diffusion when I'm truncating small things to 0 is same objective plus lambda times a 1 norm penalty. If you're a statistician, those 1 norm penalties are good because they engineer in sparsity. Call an L1 solver. Of course, if you call an L1 solver, you have to touch all the nodes. We don't even touch all the nodes because we engineer in that sparsity into the approximation algorithm. So how general is this? We don't know how general it is. We have a few other examples, which I can talk about offline if anyone's interested, but let me leave that at that. So big social graphs are a nice test case for a lot of things. So a couple weeks ago, I think David Lawler was here. So the question might be, how does this stuff apply to any other data set? So we've looked at genetics data. He was talking about astronomical data. We looked at other sorts of things. And you can imagine it's the case that if you're interested in internet advertising, you want to get throughput. You want to get a lot of people to click on something. And so if you're constructing graphs, you might want to choose, say, RBF parameters, radial basis function parameters, to be sort of large, so I can draw strength from a lot of information in terms of precision and recall. In that astronomical example, the goal was not to say, I want to classify stars into red stars and blue stars, because you can do that for 99% of the stars. It was to make a much more fine, subtle argument. And the reason you might want something much finer there is because you're going to get your Nobel Prize if you discover a new star, not if you discover that there's stars out there at night. And so you want to choose RBF parameters and engineer the graphs in very different ways. And so what we've seen in that application, other applications, is that a lot of these ideas go through using these local spectral methods and using the kernel extension local spectral methods that I glossed over to do locally biased learning on small classes in astronomical and other applications. And the reason a lot of these things work is because you have localized eigenvectors and we're engineering in statistical regularization sort of into the worst case approximation algorithms. So with that, let me wrap up and thank you for your time.